Good morning and good afternoon, and thank you for joining today's online event about HSR and PRP in substations. I'm here today with Alicia from Relyum and welcome you to listen to an interesting 30-minute presentation.
Thank you.
Welcome. Okay, today we talk about HSR and PRP, short introduction. Then we compare HSR and PRP and when to use it. Take away the complexity of HSR. Then we talk about timing, so precision time protocol and IEEE 1588. And especially there also the profiles for substations. Network recording for HSR and PRP with accurate timestamping, and then how to use it in a Velotech substation computer. Please feel free to ask questions at any time over the comment field or over the question and answer box. And at the end, we'll have some time to answer all of your questions. Talking about PRP. PRP is a redundancy protocol in substations. It's a network-based protocol, so it works on standard TCP/IP. And it connects each device to two networks simultaneously. In the substation, we talk about the SAN, which is a single attached node, which is just connected with one Ethernet cable to a redundancy box, for example. And we are talking about the DAN, which is a dual attached node, which is connected with two cables at the same time to two different networks for redundancy. You can use PRP for multiple network topologies. And the special thing about it is that each node that is connected to two networks is sending the traffic at the same time to both networks. And this means that if one network fails, the other will take over. And you have a zero delay and recovery time and zero frame loss, so you're not losing any single package. On the other side, we have HSR, which is a ring network. Also here we have DUNs, which are dual attached nodes, and you don't need switches for this one. So in this case, the DUN itself becomes a switch, and the traffic is sent from each node in a ring network to each site. So this makes sure that if one connection fails, there's still a path to the other way. So each node is sending the traffic to both sides, and at the same time you can also connect the single attached nodes over a switch and a red box and bring them inside. So even normal Ethernet devices that do not support HSR can be connected using a red box. One important thing about HSR is also that it's a layer 2 Ethernet protocol and that you don't need any software stack. Okay, Alicia, can you take over here?
Yes, thank you, Jos. Yes, in this slide, there's the representation of how Ethernet multicast traffic is sent through an HSR ring. So here in this picture, we can see how the duplicate frame isn't discarded inside the network until it reaches the last node, or better said, all the nodes in the network. In that case, it has to reach the destination, and because it's multicast, obviously all the nodes are the destination in the network. Also, it's interesting in this picture, the elements that are content on it, red boxes, to connect a single attached node, which are in the right side of the picture, and the dual attached nodes for HSR, DAN-H, which are the nodes that do the switching in the HSR ring. So next. Yes, now after reviewing very fast, the main concepts of these two technologies, let's see when you use HSR and when you use PRP, and I will start with PRP. And for a better understanding of which are the most suitable use cases for this technology, I will try to explain the pros and the cons of PRP. As mentioned by Jos, the backbone of a PRP network, the LAN A and LAN 2 and LAN B are based on standard switches. So any Ethernet switch that you may know from the market can be used in these PRP networks. That means that it's compatible with conventional Ethernet traffic, and most important, that all these layer 2 mechanisms that are already implemented in standard switches are available for doing traffic shaping in a PRP network. And this becomes very important when it's necessary to prevent from congestions in order to avoid packet loss. So these are the main benefits of the technology, but on the other hand, there's an important constraint compared to HSR, is that there's an extra cost because it's needed to do some switch acquisition, to invest in these devices in the network, to invest in engineering costs for configuring and managing this network, this central network, and for doing the maintenance of these elements. So which are the most suitable cases for implementing or for selecting this PRP technology? Well, obviously systems where there are already existing switches because they were already purchased or because there was an existing network with switches. In that case, one of the constraints is avoided. There's no CapEx cost in the implementation of PRP. Also, big systems like, for example, transmission substations that content many IDs that have to be connected to the network and inject their traffic. Well, this type of networks normally require some traffic shaping in order to avoid this congestion that I mentioned before. So PRP is very flexible in that point, and it's a very good option for using in these kind of systems. And also finally, PRP is a very common protocol, redundant protocol, that is being used for station buses. In that case, the station bus is normally a small network. It doesn't have long distances because it corresponds to all the elements that are in the control house. And in many cases, it can be covered only with 2 switches, 1 per LAN. So in that case, PRP is a very good way for obtaining this seamless redundancy without having to do a big investment in the cabling and in the devices. So next, yeah. Now I'm going to switch to HSR. I'm going to follow the same scheme for trying to explain which are the most suitable systems or use cases for this technology. So starting with the benefits, as mentioned by Jos, in that case, there's no switching devices in the network. So no extra equipment. The elements that are in the field, these dual attached nodes implement the switching functionality. So there are the switches in the network, in the ring. No extra CapEx cost in equipment, no engineering cost in having to configure or manage a complex layer 2 network. And because in that case, HSR, PRP are layer 2 protocols, so very easy to configure. And no OpEx cost in maintenance of extra devices, extra switches. So this is one important benefit in terms of cost saving from HSR. And also for long distance installations, ring topology might be better for doing some cabling cost compared to a star topology. An example for these long distance scenarios is in the large substations where there are many elements in the switch yard that have to be connected to the control house. If we have the switches in the control house, for example, in a PRP network, we have to do all this cabling installation to the control house. With an HSR topology, this is avoided. So only you have to connect the nodes among them, and it has important cost savings in terms of cabling. And a third benefit of this technology is that it has a more deterministic behavior. That means that it's easier to calculate the maximum latency in a worst case scenario because we already know that this will correspond to the total number of hops in the network. So this will be the the biggest latency in the network for a packet that has to be transmitted in the network. And compared to these benefits, HSR has a very big constraint, which is that the fact that it doesn't admit this traffic shaping based on layer 2 switching mechanisms. This was explained for PRP. In the case of HSR, even if the nodes can support VLANs or other layer 2 mechanisms like MAC address filtering or so, it's not possible to apply these mechanisms to the traffic, because the traffic has to go through all the nodes of the network to guarantee this redundancy, this seamless redundancy. And this might be a problem for some networks where there are some limitations in terms of bandwidth. So now let's see which are the most suitable use cases for HSR. So according to what I mentioned before, obviously small substations is a very good system for implementing this technology, mainly because they have a low number of IDs, so there's no high risk of congestion in the network, not very high bandwidth requirement, and even if the bandwidth is low, there won't be that congestion. So the fact that we don't have a traffic shaping mechanism is not a problem. Also process bus in a large substation. I explained it before. I mean, the ring topology implies some important cost savings in the cabling of the network. And also HSR is becoming more and more popular in some renewable plants like wind farms. The particularity of these power plants or power systems is that they're normally simpler, they are more self-contained, so it's easier to manage the bandwidth and the maintenance of these particular systems. So now let's move to the next section. We know that there are some doubts about HSR because there are some limitations that sometimes engineers don't know how to face. So now I'm going to try to focus on these constraints, mainly in three of them, well, the three main constraints of HSR, and explain which are the solutions that are offered by the standard to solve any problem that we may have. I will be talking about latency, bandwidth, and maintenance. So starting with latency, compared to a PRP network with a central switch, in a ring, in an HSR ring, the packet has to go through many elements, so it has to go through many hops. In order to avoid a big latency due to those hops, the standard defines the cut-through mechanism. To understand cut-through mechanism, let's see the structure of the HSR frame. In PRP, the standard introduces a PRP trailer at the end of the packet. But in HSR, we're talking about the HSR header that is introduced just before the original Ether type. That makes that when the red box has to process the frame in order to determine where it has to be sent in the network, it only needs to process the first part of the packet to switch quickly to the next hop or to the next link. So this is the cut-through mechanism, and the opposite one is the store and forward, which is the most traditional one. And I'm here introducing some examples of our technology. For a packet size, a big packet size of 1,500 bytes with a very low throughput today, 100 megabit per second. With the store and forward mechanism, we would have a switching time of 13 microseconds. While with cut-through mechanism, we will have to process only the first part of the frame, and we will reach a switching time of one microsecond. So there's a big difference. And this leads to, with, for example, a maximum latency admitted of 1,000 microseconds, that would correspond to the worst case scenario, which is the case where the packet has to go through all the nodes of the ring. We will be able to install up to 7 nodes in a store and forward system with these conditions, packet size and throughput, while with cut-through, we will be able to install up to 74 nodes. However, there are other considerations that we have to take into account with these calculations. Most of the frames don't have the maximum packet. For example, with sample values, we have around 160 bytes frames. And this makes that we can reach up to 40 nodes or so with a store and forward and a low bandwidth network. And also, of course, we have to consider that today, most of the devices already support 1000 megabytes. So in summary, the latency is not a problem in HSR in today's networks. Now let's focus on bandwidth and maintenance. Bandwidth can become a problem in a low throughput network because we don't have these traffic shaping mechanisms. So there might be congestion and there might be packet loss, which is not acceptable in this type of networks. And also we have to consider maintenance in HSR because if we need to do some shutdown in an ID for implementing some maintenance task, we have to take into account that we are switching off one of the switches or the elements of the ring. So if we have, for example, to shut down 2 or more IDs, we are compromising the communication in the network. So for facing these two aspects, the standard already defines a different traffic shaping and segmentation based on mesh strings and combined topologies. So what are mesh strings? Here in this slide, we can see an example, very simple example, where we have 2 rings, ring 1 and ring 2, connected among them with quad boxes elements. We need 2 quad boxes in this topology to avoid single point of failure. And what quad boxes guarantee is that if we have to switch down all the elements in ring 1 for example, maintenance task, the communication in ring 2 is guaranteed through the quad boxes. And in the same way, these quad boxes can limit the packets or the throughput that goes from one ring to another. So they implement a kind of traffic shaping for preventing from congestion. And the good thing is that this is a very flexible standard, very flexible topology. And in the right side of the slide, we can see 3 rings, but we could have 4, 5, well, an unlimited number of rings in these topologies. And also we have another element, which is combination of protocols in the next slide that can help us to do this traffic shaping and segmentation. Here you have the typical topology with one PRP network connected to one HSR network. In the middle, in the point of connections, we only need normal red boxes. And this topology guarantees that they are independent in terms of maintenance and in terms of traffic transmission. And this is a very typical configuration proposed for substations where station bus is implemented through PRP and process bus can be implemented through one HSR ring or different HSR rings. Okay, so now I'm going to talk about another very important concept that is related with HSR and PRP and with some critical sectors like, for example, the electrical one, and is the synchronization. In particular, PTP, the standard defined in the IEEE 1588 standard. This document defines how synchronization works in general terms, and the profiles explain how it is implemented in each sector. So for example, for substations, the standard that explains the implementation of PTP is known as power profile, and it's defined in the document IEEE C37.238. In parallel, the standard that defined and explained how to implement HSR PRP included an Annex B, for explaining how to implement PTP over this kind of redundant networks. And this was known as industrial profiling. And after that, the group that was defining 61850 standard took some ideas or most of the ideas of the previous documents and defined the power utility profile in the standard 61850.93. That is the one that is recommended for this type of networks. So which are the main components of this standard? We have the transparent clock mechanism that is implemented in the switches, and it it's implemented for correcting the time references in the switches. This mechanism takes into account the transmission time and the switching time to correct the time reference that is transmitted in the network. Also, we have ordinary clocks that are implemented in the slaves, that is in the end equipment. We have one or two master clocks in the network, sometimes more than one for redundancy. And these devices take the reference from a GPS receiver and transmit this reference through the network. And we have also boundary clocks, that is the mechanism that defines how to implement gateway functionality between different clock domains. So now just a quick overview of how synchronization is implemented, how a slave clock has to synchronize with this protocol. So on one side, we have the grandmaster device that gets that GPS reference from the receiver, and it transmits a PTP supervision frame to the network. When this PTP supervision frame is received by a switch, this switch has to apply a transparent clock and correct the reference before sending again the PTP supervision frame to the other links of the network. And finally, the slave, the end equipment that has to synchronize with this time reference implements slave clock mechanism for getting this time reference and synchronizing its CPU with the network reference. So once I've been reviewing the most important concepts of HSR, PRP, let's go to the next slide, which is very significant because it shows how the standard cover different topologies, different aspects of redundancy. Here we have an example with two PRP networks. You have ID1 and ID2. Each network has different grandmaster reference. They have probably two devices with two GPS. So they send their own PTP supervision frame to the network. And in the middle, between the connection of the HSR ring to one of the PRP networks, we have red boxes that are implementing boundary clock. So there's a two-way transformation between PRP and HSR, and also between the two time references. So the good thing of this standard is that it covers multiple implementations of the redundancy in different systems and in different scenarios. It's a very, very open and flexible standard that can cover many needs in critical systems. So now, after reviewing the concepts of PTP, let's talk about some new devices that are appearing in these kinds or together with this transformation or evolution to smart grids. Compared to legacy systems, to legacy substations, where the electrical engineers used to use analog signals for analyzing the grid, with the new digital scenario, the data information is sent with Ethernet packets. So these new systems demand network recorders that are capable to capture traffic, to timestamp that traffic with a network reference, in that case with the PTP reference, so with a determined accuracy, and probably they would need hardware timestamp for being able to use this reference correctly. And they need tools for analyzing it with the IT elements that are already available in the market, for example, Wireshark. So in the next slide, please. This traffic recorder, network recorder that I mentioned before is very useful in different use cases. For example, in laboratories where engineers have to perform the ID function test, protections or so, where system integrators may need to do some integration test, FAT acceptance test, and so. But also, this new device, compared to other testing tools that were traditional in the market, allows being installed in standalone mode. And this is very important, for example, for performing some commissioning testing based on the exchange of IEEE 61850 traffic and data among the different IDs, but also for measuring different communication parameters that are critical in this kind of networks. For example, the latency, the redundancy, the behavior of the communication in case of a link loss, the behavior of the synchronization in case of loss of global time synchronization reference or so. And finally, why not? Device upgrading is becoming very common in digital systems with cybersecurity new requirements, for example, also device replacement, configuration upgrades. And these devices can be very useful for implementing even remotely this task without having to send technical people to the substation to do this small testing of performance after or before an upgrade, for example. And these were like the more traditional testing that we know until today, but we have to consider another scenario where this traffic recorder can help us. And it's the case when we have one of these devices installed in standalone mode and doing continuous monitoring the network. And if we are capable to trigger conditions based on the packet inspection of the network, these devices can help us to detect in advance some failures and even helps us to analyze them and debugging easily. So we have to consider all these new functionalities or all these new uses that are available with these network recording systems. But for being compatible with the new networks, let's see in the next slide, which are some requirements that are related with these new testing tools. We have been talking about HSR and PRP networks and PTP. So obviously, compared to other PCs with Wireshark and other analyzing IT world analyzing tools, these new devices have to be capable to connect to redundant networks. They have to be capable to implement this dual attached node, and they have to be capable to support these special topologies. Of course, they have to be able to synchronize with the PTP reference of the network. And not only that, the important thing is to timestamp the traffic recorder with the reference of the network and with a very good accuracy so that the latency and other parameters can be measured correctly. And finally, of course, all these new elements with all the cybersecurity concerns that we have at the moment have to support cybersecurity mechanisms defined by utilities like remote monitoring, access control, port enabling, disabling, and so on. So now I'm going to let my colleague Josh to continue with the next slide about all elements.
Thank you, Alicia. A great introduction of HSR and PRP. So today, I also want to talk a little bit about our substation computer and how to use HSR and PRP inside. So together with Relyum, we are able to put a PCIe card inside that is transparent to the system, so you can have it available for any operating system like Linux and Windows. So you are merging OT and IT capabilities within a substation server. With doing that, you have a lot of computing power, but at the same time, you can integrate in traditional OT networks. You have additional IOs, you have time synchronization, and with the onboard TPM 2.0 module, you also have hardware-based security. So this means you have seamless redundancy, you have IEEE 1588 support, which is hardware-based, and you have a fully IEC 61850-3 certified system. So what does it mean? The computer becomes a dual attached node for HSR networks, or if you are using it mainly in the station bus, it becomes a dual attached node for PRP networks with hardware support, so you don't need to take care of the software itself. This is quite important because what we hear from the market is that many software implementations of PRP are not working as reliable as requested. This means you have a seamless support. You don't have much configuration. You don't need to take care of this. And you have the synchronization for Windows, for example, where Windows can get the time stamping from the card and get a much better synchronization compared to a standard NTP time server connection to external clock. In addition to that, you can monitor the system with SNMP, you have a syslog, and you have some kind of integration and synchronization. So thank you very much for listening to today's webinar, and now we have time for questions and answers. So at any time you can still ask questions, and Thomas, do you have the first ones for us already?
Yes, I do. The first question is from Suraya. May I please know what do you mean by switch acquisition? I think I take that one. It just means the cost of buying switches. Omar has a question. I think it's for Alicia, or a couple of questions actually. One is HSR is based on layer 2 protocol and PRP is based on layer 3, right?
No, in fact, the two are based on layer 2. The two work at Ethernet level, and it is one of the benefits in terms of management and configuration, and also is the fact that it can be implemented in critical and with low latency networks.
Okay. He would also like to know if the HSR packets are moving like tokens.
I'm not sure what it means moving like tokens.
Me neither, unfortunately.
Well, the thing is that it's transmitted, it switches from one node in the ring till the destination. So there are two duplicated frames, one in one side of the ring, the other one in the other side, and they are not discarded until they reach the destination. The first one is accepted and the second one is discarded. So I presented the example of multicast because there you can see that until it goes through all the rings in the network, the two frames are not, or the second frame is not discarded. So this is the concept. But the red box, the node, gets out the trailer or the header in the case of HSR, and it becomes a normal Ethernet IP frame for the device. So this is one of the goals of the simplicity of the protocol.
Okay, thank you very much. Austin would like to know, in case of jitter and latency, how does the system cater argument for this?
Sorry, I couldn't hear you very well, the question.
In case of jitter and latency, how does the system cater for this?
Latency, well, one of the benefits is the fact that it's a layer 2 protocol. This is one thing that it's very positive for the latency. I mean, because you don't have to process by software or at layer 3 the packet. And as I explained, in cut-through, with cut-through operation in HSR, where you have to go through many hops until the packet reaches destination. The processing time is around 1 microsecond. So this is the key element of latency. And well, this is why this kind of redundant technologies is used in, for example, in smart grids. I mentioned the maximum latency of 1000 microseconds. This is based on the standard for a protection reaction that has to be under 3 milliseconds. So I consider 1 millisecond for the packet to get to the protection, one more for being processed, and one more for opening the controller. So there are protocols focused on low latency applications, and this is one of the reasons why they are mainly implemented by hardware in a special technology in FPGAs. I don't know if I was able to answer it.
I think so.
Well, if they want some information about switching latency and jitter, I mean, there's I don't have here the information, but I can share the information. Just in order to understand that, it's related with the fact that it matches very well with PTP, for example, that demands in transparent clock around 50 nanoseconds accuracy. So it's a well-defined protocol for this kind of critical systems.
Okay. The next one I think is for Jos. Jose would like to know, do you have any implementation example with the RSA PC?
Yes, of course. So we have multiple HVDC installations all over Europe. We also have installations in transmission grids for transmission substations, where we use it as PRP or HSR node. This is through transmission grid operators in Europe, South America, Middle East, and Asia. So there are plenty of examples. If you want to have more details, just write an email and we'll reply to it, and can probably also go into a discussion.
Okay, thank you. Do we think we still got time for 2 questions? Because then we could get through all.
Yes, let's do it.
Okay, Yusuf would like to know, using industrial switches, can we run duplication and deduplication in order to run these networks with more than 30 nodes for store and forward?
If we talk about industrial switches, I think we are talking about PRP. I mean, the standard switches. I suppose we are talking about this technology because, I mean, in HSR, we don't have industrial switches. So there you can have a larger number of nodes because it depends on the topology of the backbone. I mean, you might have 100 of nodes connected only with 2 or 3 switches in the backbone of the network, so there's no problem on latency or so. The central switches doesn't implement duplication or discarding of the frames. This is implemented in the dual attached nodes. So many devices, IEDs already support this red box technology. And this is the case of the computer that explained Josh. Or if you don't have it already in the device, you use in the middle a red box device that implements that duplication and discarding when receiving the duplicated packet. So the fact that 2 packets are transmitted in 2 networks is transparent for the networks. In fact, the 2 networks are separated. They are not connected. So only one packet goes in one network and another packet goes in the other one. So there's no conflict on duplications or so.
Okay, and the last one, is it auto configuration, and how long does it take to be fully operational?
Auto configuration in terms of
I think like when using HSR or PRP,
okay,
the
yes.
configuration that is needed.
Well, this feature of duplicating and discarding a card is completely transparent for the rest of the devices. I mean, it's an algorithm that is defined in the standard. So the only configuration needed is the IP address and the port and the VLAN. I mean, the same configuration that would be required with a standard network. And then the device that implements the red box technology is in charge in layer 2 to separate in 2 frames and discard the duplicated frame when received the 2. So it doesn't need any special configuration. I think in terms of auto configuration, it's more about if you switch on a device, the time that the system takes to start running than this mechanism that is done almost automatically, because in our case, it's done in an FPGA. It's not a software implementation as just mentioned. So it's like if it was an ASIC, it doesn't need any configuration. It's automatically done. I don't know if it responds. I've been able to respond it.
Okay, thank you. And with that, I give back to Jos.
Okay, thank you very much, all of you, for joining today. If you have any further questions or your questions were not answered the right way, please write an email to Alicia or me. Our email addresses are there. We'll also follow up afterwards and send you the presentation. My colleagues will do that. And I hope that we can see you again on the next webinar. Thank you very much for joining and see you soon. Bye-bye.
Thank you. Thank you all.